So I wanted to show you an interesting way to do this maximum range problem. It's not an analytical solution. It is a computational solution that starts with some analysis. So what I did here was, as you can see in this picture, I took our two premise equations of motion. We're using that y initial and x initial are zero, so putting the origin at the launch point, and therefore we had that the ax term goes away, so just vi cosine, there should be a theta there, t. And then yf equals yi, which goes to 0 since I'm starting it there. So yf is going to be a negative number since I'm going to land below. Vi sine theta t minus 1/2 gt squared. I already did the plug-in. And what I did is I solved this for 0, moving everything over onto the left side, and then solve for t using the quadratic equation, and then put it into that expression. And then, so what I would have here is, we're going to get rid of the negative because I am looking for a max, right? I have the first term is vi squared sine theta cosine theta g, and then plus, and then vi cosine theta times this thing in the square root. So I've got that expression, and I want to maximize x. So technically what we should do here is take the derivative of this with respect to theta, set it equal to 0, solve and do an analytical solution. Let's do a computational solution instead. You'll notice I have essentially 4 variables in this expression. And I've written this expression out. Oh, it's horrible here. I know that there's the final y position, there's the initial speed, there's the acceleration due to gravity, and there is the angle in degrees. So when you're programming things into Excel, some people like to put in big, long equations like this. I think that that's a terrible idea, right? Instead, what I like to do is I like to calculate the parts and then assemble it. Because in Excel, I can always later hide my work, right? I can actually just group all of these things. And if you go, group all of these, and if I want to hide those columns, I could just hide them so people wouldn't see the work. But I think it's easier just to do little bits and pieces as you go along. And the nice thing about Excel is we can create then a structure where we can vary the outcome and test different solutions. So if you notice, my major components here in this expression are the sine of the angle, the cosine of the angle, that first term, that vi squared sine of theta cosine of theta divided by g. Then there's the coefficient of the second term, which is vi cosine theta over g. And then there's the thing inside the square root, the vi squared sine squared theta minus 2 times g yf. And so let's see what I did. So first here, I just made the degree measure 0.1 in degrees. Then you'll notice here, sine. Well, Excel always does things in radians. So I need to do the conversion so that it takes the input in degrees and calculates it correctly. So you'll notice I took the input from cell A8, which is the angle in degrees, and then I multiplied it by pi and divided by 180. So that gives me the correct angle. Do the same thing here with cosine. And then the first term, let's see what I did. I took B2 times B2, right? So that's initial position of 2, or initial speed times initial speed, which is correct, times C8, which is this here, the cosine, times B8, which is the sine, and I divide it by B3, which is the acceleration due to gravity, and that's my vi squared sine cosine g equation. So that's the first term. Awesome. And then the coefficient here is vi cosine t over g. So vi, which is B2, cosine, which is the C8 column, or C8 cell, divided by B3, which is that. Cool. And then the thing underneath the square root, I have vi squared, so B2, and then times sine squared, and so that is B8, which is correct there, minus 2 times the g, which is in cell B3, times yf, which is in cell 1, and then took the square root of that. And then I multiplied, or added, the second term then, that should be a multiplication. Yeah, caught my error there, right? So I added those two terms together, the coefficient times the square root, and then the range is the first term, D8, plus the second term, G8. So there you go. Now, the great thing here is I can now copy and paste all that and then test every possible angle. I just have to change some of my formulas. Let's see what happens here. If I put 0.2 there, what I can do is highlight the cell, drag, drop. Now let's see what happened here. The value changed. You'll notice where this was A8, this has become A9. That's good because it refers now to this cell. So I want to do the same thing. But here I have a bit of a problem because I always want it to refer to cell B2 because when I drag this down here, if you notice what's going to happen is it changed it to B3. I don't want that, right? I always want it to refer to B2. So here's what we do. If I always want it to refer to B2, I just put a $ in front of the B and the 2. That means that I don't have to put the $ in front of the B. That would only change if I try to drag to the right. In fact, let's just not do that then. Let's see, B2 and B2. So when I drag downwards now, I just want to show you what happens. Still a problem, we'll see why. The B2 stayed the same. The problem was the C9. Well, that's actually good. I wanted it to still refer to 9 because I wanted to have the cosine of this new angle. But what changed was the acceleration due to gravity. So what I need to do is lock that in as well at B4. So what I need, or B3, what I need to do is always lock in these three terms and then let everything else float. So here we go with this. That means I'm going to lock in the B2 and lock in the B3, but I want the C8 to float because I want that to catch the thing that's in cell 9 then. And the square root, all right, once again, everything with the 2's and the 3's I need to lock in. And the 1 actually there too. All right, boom, and there we go. And so the second term, I actually want those to be the things in row 9, and then I want these things to be in the row 9 as well. Okay. All right. And you'll notice then when I increase the angle, the range increased, which is something that we should expect. All right. So now what I want to do is essentially test this at all possible angles. And so here's the neat thing. Once you have a pattern established in Excel, so 1 and 2, I outline both of them, and I just do this, watch that. It just literally copies that. If I were to, let me just grab that and get rid of it. Just grab cell 2 and go, it would just copy that. I don't want that, right? Undo. But when you establish a pattern, it assumes the same arithmetic pattern. So I'm just going to go all the way down to 90, or 89.9 really. So we can see what happens. Boom, there we go. Now I can make that more granular if I want. I can go by the hundredths. I would just need to use more rows, that's all. And so all I'm going to do is just take that equation and boom. See, it just populates all those numbers. It's dragging all those equations down. So here I go, here I go, here I go, all the way down, all the way down, all the way down. All right. And so now really all we care about, as I said, was this last column. So I'm going to hide some of my work. I want to hide these columns. I don't want to hide the B column because I put those there. I probably should have moved everything over so that that's not true, but let me get rid of this because it's a little distracting. And hide those columns. Boom. See, I'm hiding my work. And as what you can see here is that range is still increasing, 2062, 284. Here, there we go. Let's find the range 83, 83, 83, 83, 84, 84, 84, 84, 84. 84s never gets up and goes down to 83s. So let's look to see where it stops increasing and starts decreasing. That's an increase, that's an increase, that's a decrease. There, folks, is my answer, at least to 3 sig figs. Isn't that neat? Now, watch this. So that is the answer with a certain set of paradigms. That's with an 80-degree launch angle. That's with all these parameters. Watch this. If I make this a 100-degree launch angle, let's see if we can find, let's go to our previous answer of 17.4 and see if it's the same. 7.4, No, 17.5 gets bigger. And so I'd have to come down here and just like take a look. Oh, it looks like the 2676 is where it's peaking there. Let's look and find a more granular answer. Oh, there it is, 20.9 with that. I can also change that hill height. So minus a 400, boom. And now we can see where that maximizes. Seems to still be going up there, 1300s. Oh, somewhere in the 1300s is the maximum range. And so I can hunt and peck and find where that 32 is the largest 32. It looks like that one right there, 36.8 degrees is my winner. So an interesting computational solution. Once you've done enough analysis that you have an equation that's really difficult to manipulate, you can let Excel do the work for you. So this is an interesting little way of solving these sorts of problems. This is the sort of modeling that scientists do all the time. If they're not looking for an analytical solution like an equation, like they just want an answer. So there you go.